Okay, now we're going to be looking at problems involving two strings or springs connected together, right? Okay, so let's have a look at this question here. We're told two identical elastic springs, P, Q, and QR, each have natural length L, modulus of elasticity 2 mg. The springs are joined together at Q. The other ends P and R are attached to fixed points, with P being 4L vertically above R. Particle of mass M is attached at Q and hangs at rest in equilibrium. Find the distance of the particle below P. Right, okay, so what's going on here? Okay, so we've got these two springs, P, Q, and QR, and they're connected together. So what's happening is, for the first one, PQ, again, what's going to happen is sort of going to hang down from a fixed point P like this and then it's going to end at a point Q. Then I'm going to do it in red. The other spring it's going to be like this, and then it's going to end at another fixed point R. Okay, so hopefully you can see that right. So we've got these two strings in black and red, and they meet at the point Q. Okay, hopefully happy with that. Now, at Q, there's a particle attached at the point Q. So this particle here, or sort of a ball there, and this ball sort of connects the black and the red string together. Now, to visualize this, if it helps, I've got this picture here. It's sort of like a bead, right? So we've got this bead in the middle, and it's between the blue string at either end. That's sort of the situation here. So we've got this sort of particle this in the middle, and it's it's between two strings. Okay, so there we are. Right, now we need to add on our forces. So to help visualize exactly what's going on in terms of forces, let me break it down. Let us consider no particle added on. What's going to happen then in that case? So before we add any particle on, the strings are going to look like this. So again, from P, going to droop down, and then the red string is going to look like this. And you can spot there's a gap between the black and the red string here. Okay, this is before we add any particle on. Now let's say we do add our particle. Okay, so in order to join the black and the red string, then obviously they're not connected at the moment. What's going to happen is firstly the black string is going to extend downwards to meet the particle. Likewise, the red string is then going to stretch up to meet the string as well, to meet the particle as well, right? So essentially what's happening is, to sort of help visualize it, you've got this picture here. So in this picture, we've got this man that's pulling two strings together from each end. Okay, so you can see that the particle, the ball, is essentially acting like the guy here. It's sort of pulling these two strings together. So it's stretching the two strings together. Okay. And so what that means is, well, for the black string, firstly, it's going to be stretching down to the particle. And then for the red string, it's going to be stretching up, okay, to meet the particle here. Okay, hopefully you can see that, right? So that means in terms of forces, well, firstly, for the force in the black string, if the black string is stretching down, to oppose that, the force in the string is going to act up. I'm going to call that T1. Okay, my tension force. Likewise, and for the red string, the red string is being stretched up, so the force in the red string is going to act down to oppose the upward stretch. I'm going to call that T2, tension T2. And so there we are. So those are my two tensions. Okay, again, they're going to be different because the strings are different here. Okay. Now the final force is actually going to do with the weight of the particle, right? Because we're told the particle has mass m, so the weight of it, which will pull it down, is going to be mg, right? So mg there. And those are all my forces. So hopefully that made sense. Okay, so there we are. Now we need to add on some lengths. Okay, so firstly, okay, if this is, so this, let's say that's the natural length of the black string, and then this is the part that's been extended or stretched to the particle. I'm going to call that x then, right? Likewise then for the red string, again, this is let's say this is my natural length. Both have the same natural length here, okay? Both strings have natural length L, right? But then this extension is going to be Y. So this bit that's extended up is going to be what I'll call Y, okay? Hopefully happy with that. Now, what we also know is the total length, okay, from top to bottom. It's 4L, okay? Because we're told P is 4L vertically above R. So from P to R, it's 4L, okay? And so that's everything I need to add on then. So hopefully you're happy with this diagram with the forces and the lengths at play here, okay? I'm going to get rid of this left diagram. I'm just going to work with the right with this diagram here. So firstly, what I can do now is again look up and down, resolve up and down. Well, firstly, I've got my tension T1 upwards. That's going to equal the downward forces, which is here. So it's the weight mg, add on the tension T2, okay? That's from F equals ma, right? Now, what I can also do then is also use Hooke's law, so T equals lambda x over L, I'll box this. I can use Hooke's law for the black and the red string separately, okay? So firstly, so from P to Q, right, so the black string, firstly, if I use this Hooke's law equation, well, for the black string, it's T1. That's going to equal lambda x over L. Well, lambda is 2mg. That's my modulus of elasticity times the extension of the black string, which is x, over the natural length L, right? I can then do the same for the red string from Q to R, right? And for that, well, the tension is T2. And again, that's going to equal lambda x over L with 2mg times the extension, which is y. Okay? Over L. Okay. So from these three equations I've got here, what I can do is I know what T1 and T2 are. So I could sub it into here. So therefore, T1, which is 2mg over L, that's going to equal mg add T2. So mg add T2, which is 2mgy over L. What I can do to simplify it, well, I can get rid of the fraction by multiplying everything by L, both sides. So therefore, I get that 2mgx is mgl add 2mgy. Okay, and actually then I can cancel the mg's. So therefore I get 2x is L plus 2y. And that's a lot nicer, right? Okay, so that's really all I can do. Except I've also got all these lengths to work with. Now remember, I can consider, if I look at all these lengths, right? I know that all the individual lengths, right? So the individual lengths, that's going to be L plus X plus Y plus L, has to equal the whole length of 4L, the whole thing. So hopefully then you can see, well, if 2L add X add Y is 4L, Therefore, x plus y is going to be 2L, right? And so we can rearrange. So let's say y is 2L minus x. So what I can do there is sub y into the equation I've got here. So then that means 2x is going to be L and 2y, which is 2 lots of 2L minus x. Okay, and so if I expand this, I get L plus 4L minus 2x. I can then add 2x, so then I get 4x equals 5L. Therefore, x is going to be 5 over 4L. And so that is my extension x of the black string. So then if x is 5 over 4L, I can add that on there. Again, the diagram might not be to scale. That's the malloc, just a rough diagram. But that is my that's my extension of the black string there, which is x. Well, we're pretty much done because the question has asked me to find the distance of the particle below P. In other words, the distance between P and the particle, which is going to be this purple length here, from P to the particle. Okay. Well, the distance then, well, it's going to be this L add 5 over 4L. Well, L add 5 over 4L, that's going to be 9 over 4L. And there we are. So the distance is L plus 5 over 4L, which is 9 over 4L. And there we are. That's the distance from P to the particle. Cool. Okay, so we've got this question here. So firstly, we need to find the distance of the particle below the ceiling in equilibrium. So what exactly is going on? What do we draw here? Okay, well, we have this spring which has natural length 2a. So this is my spring initially. The length is 2a. So that's before we add any particle on, right? But then we do add a particle on. So this is my spring, and we add a particle in the middle, in the midpoint, okay? Like this. And so what that does is split the spring into two parts, a top and a bottom part. And so that means effectively the natural length halves. So the natural length of each individual, the top and bottom part, would just be A. Okay, so 2A for the whole spring, but then we effectively split it into two like this. So the natural length of the top and the bottom part is just A here. Okay. But that's not all that happens. We then obviously the spring at the top and bottom are also then attached to fixed points like this, and so point A is on the floor. So A is the fixed point here, and B is then at the top at the ceiling there. So hopefully you're happy with that. Okay. But then obviously what also happens is the particle has a weight of mg that's going to act down. It's going to pull the particle down. So what happens is initially, yes, we put the particle in the middle, but then once we kind of let go, the particle sort of naturally droop down, again due to the weight. So the particle will then sort of droop down and it'd be somewhere down here, right? Along the spring. So that's where it will sit in equilibrium, right? So there we are. Okay, so then in terms of forces, well, again, the particle has its weight of mg acting down. And then in terms of the two tension forces, so the tension, the top and the bottom part of this spring here, well, for the top part, again, it's the same story as with the last example, where the particle is sort of stretching the top and the bottom strings towards it. So that means for the top string here, it's being stretched downwards towards the particle, and so that means the tension in the top part is going to act up, and this is T1. Then for the second string at the bottom here, again it's been stretched up towards the particle, which would mean that there'd be a tension force acting down. Okay, and that'd be T2. So that's the story, right? The same sort of situation as with the last example. So hopefully happy with that. And then lastly, we need to add our lengths. So obviously the top and the bottom part will have a natural length. So let's say here, this is my natural length. Now the natural length, of course, would be A, not 2A, because again, the spring is split into two parts, the top and the bottom. So the natural length is split up. Okay, and then there'll be an extension of X. Okay, and there we are. Then obviously for the bottom string, then again, that's there's going to be a natural length of the same natural length A, and then an extension towards the particle of Y. Okay, a different extension. Okay, so hopefully happy with that. And lastly, we also know the total height, okay, from top to bottom, because we also know the height of the whole room from ceiling to floor is 5A. So we can add that on as well. And that's everything we can do, right? So hopefully you're happy with this setup here. Okay. Now, we can resolve up and down. So again, I've got my tension force here, T1. And then that's going to equal the downward forces, which is mg, the weight, and the tension T2. There, okay. Again, we equal the top and the bottom forces because it's an equilibrium. So the opposite forces equal one another. Okay, there we are. Then we can also use Hooke's law, and we can use Hooke's law for the top string and the bottom string separately, right? Just like the last example. So firstly, the top spring, sorry, for the top spring. Well, the force is T1 at the top, so there we are. The modulus of elasticity is 2mg times the extension, which for the top part is x, right? Divided by the natural length A, okay? And then we could do the same for the bottom. And so here, well, the force is T2 in that spring. And so again, 2mg times the extension y, okay, over the natural length A, okay. Right. Okay. Now we know what T1 and T2 are, we can substitute it into this equation here. So if T1 equals mg at T2, so T1, which is 2mg x over A, equals mg plus T2. And then we can sort of deal with this, right? Let's simplify it. Well, firstly, we can get rid of the fractions by timesing everything by A. So 2mgx equals mga plus 2mgy. Then we can cancel the mg's in all the terms by dividing by mg. So then we get 2x is a plus 2y. Okay, hopefully happy with that. Then I can just rearrange. Let's rearrange for y. So 2y is 2x minus a. Therefore, y is going to be half of this, right? We can expand it. So that would be x minus a half a. And there we are. And so y here, well, I can say y is x minus a half a. Yeah, right? So there we are. Now, the distance they want me to find is the distance of the particle below the ceiling. In other words, they want the distance between the particle and the ceiling. Okay. So they want this distance here. Okay. And then hopefully you can see that the distance we want is a at x. Okay. But I need to find x in terms of a. Okay, I'm going to need to find something for x. Now, to help me with that, I know that if I add all the individual lengths here, that's to equal the total length 5a. So therefore, I can also say that that a plus x minus a half a plus a has to equal 5a. And so then I can sort of solve for x here. So if I simplify it, I get 2x plus 3 over 2a is 5a. So 2x is going to be 7 over 2a. Therefore, I can divide by 2, so x is going to be 7 over 4a. Okay? Cool. So now there we are. We're pretty much done now. So if x is 7 over 4, then the distance we want, which again is a at x, is going to be a plus 7 over 4a, which is 11 over 4a. And there we are. Cool. Then in part B, we've got this weird one marker. So we're told in reality the spring may not be light. What effect will the model have had on the calculation on the distance we found just right between the particle and the ceiling? Okay, so here we're told the spring is modelled as light. Now that will be the assumption that'll be the assumption for every sort of spring and string in this chapter. All of them will be light. But what that means is, if you think back from normal maths, light means no mass. And that kind of makes sense sort of in real life. If something is light, it's not heavy, right? So there we are. Which means if it had no mass, so if a spring is not light, it will have mass. And therefore, it would also have a weight, okay? Therefore, the spring would have weight as well. Obviously, that's because weight is mass times g. So if you have a mass, then there's a weight that exists, okay? Now, because if the spring has a weight, well, every weight force acts downwards, right, due to gravity. Which would mean the particle then, if we add in another force downwards, it's going to sort of like push down the particle even further down, right? So what that would mean is, therefore, the particle would move further down the spring, okay? And so then what that would mean is, as a result, the particle is further away from the ceiling. So that means the distance would increase. So the distance from the ceiling would increase. And there we are. Okay, got this question here then. Okay, so again, it's going to be a similar situation to before. What's happening here is, again, they've got this string hanging down and then the particle at the end. I know it's going to look like this because we're told a particle is hung at the end here. So the end here is going to be D, right? So what's happening is, essentially, at the top end is going to be A. That's the fixed point. So A is the fixed point. And so we've got basically two strings connected together again, AB and CD. So what's happening is, the first string is going to hang, it's going to go down to a point B, okay? Then that's when the next string comes in. I'm going to do that in red. And then that's going to go, well, this string then starts at C. So actually B and C are actually the exact same point. And then the red string goes to the point D. Okay? Hopefully with me here. Then at D, that's where the particle is. Okay? Now the particle has a mass m, so the weight pulling it down is mg. Okay? So what's happening here is, this is where it kind of deviates a little bit from the other questions. In the other questions, the particle was in the middle, which split the string in two. But here, the string is sort of connected to make just one long string, because the particle's at the very end. So what happens here is essentially there's just one tension force. Obviously, it's going to act upwards because it's going to oppose the downward stretch. Like this. And there we are. So that means in each of the black and the red strings, the tension is going to be the same. And actually, if we just resolve up and down, we can see that T is indeed going to equal mg. Okay, so there we are. Okay. Now I'm going to add my lengths on. I'm going to add my lengths. So again, firstly for the black string, again, it's going to be some natural length. Let's say here. So the natural length is L, and then it extends until then it connects to the red string. I'm going to call that extension X, and then likewise for then the red part, again, it's going to be some natural length L, and then it's going to be some extension Y of the red string. Okay, so again, hopefully happy with that. Okay. Right, okay. So there we are. Now we're just going to be using our formula. So again, we already know that the tension in both of them is mg. Again, it's sort of because the force, it's because they sort of act as one, because the force, the particle isn't splitting them in the middle. So there we are. Okay, now I'm going to use T is lambda x over L. And again, for the black string, so from A to B, again, I know that T, which is mg, is going to be lambda. Now, for AB, then the modulus of elasticity is 2mg, okay? Times the extension x over the natural length L. Then, for the string C to D, again, the T is going to equal lambda x over L. T is mg. That's going to equal, well, for the string CD, the modulus of elasticity is 4mg. And the extension is Y, okay, for the red string. And the natural length is L. Yes, they have the same natural length, okay, so there we are. And so then at that point, it's just algebra. So again, I can equate them together because they're both mg, they're both equal. So therefore I can say 2mgx over L is 4mgy over L. And simply, if I just multiply top and bottom by L, I can deduce 2mgx is just 4mgy. And so very simply, 2mg, 4mg gets me x is 2y. So I can cancel it down. Okay. I can cancel the mg's. So 2x is 4y. So then x is 2y. If I just break it down there. So there we are. So that means if x is 2y, we can say x here is, well, 2y, right? So the distance they want the length AD. So they want the this distance here, right? This whole distance from A to D. That's what they want. Okay. Okay, so then the distance then is going to be L and 2y and L and y, right? So L add 2y add L add y. That's going to be 2L add 3y. Well, the issue is I need to find y, well, in terms of L, right? I can only have L involved. I need to find y. So I'm going to have to kind of sort of go back to the drawing board. I can't come up with any other equation. I've already used F equals ma. I've used my two tension equations from Hooke's law, and I'm not given any lengths to work with. Okay, these are the only lengths I'm given. Okay, so if I look at the equation with y, if I stare at this one, I can actually simplify it. So I can say that if I do it in red, if I get rid of this, I can say that mgl is 4mgy. And so then the mg's cancel, so therefore L is 4y. So therefore y is a quarter L. And now we got somewhere. Okay, cool. So now I can work out the distance in terms of L. So now 2L add 3 lots of a quarter L. So 2L add 3 over 4L gets me 11 over 4L. And that is my distance from A to D. Okay,